You probably think of silicon as the thing that powers our computers, right? The brains of the operation. But what if you could reshape it, literally atom by atom, and make it do things you never thought possible? Well, today, we're diving into how electrochemistry lets us do just that, sculpting silicon into incredible, microscopic structures that can do amazing things, like glow.
So take a look at this. How on earth can these two things, on the left, what looks like a dense forest of tiny pillars, and on the right, something more like a microscopic sponge, be made from the exact same material? We're talking a simple, plain old silicon wafer. That's the big question we're digging into, and the answer is hiding in two really clever electrochemical tricks. Okay, so you might be thinking, why even bother? Why take a perfectly good piece of silicon and just carve it all up? Well, it's because when you get down to the nanoscale, materials you thought you knew can suddenly get brand new superpowers. We're talking about unlocking possibilities that we're really just starting to wrap our heads around. And the applications here are huge, from making solar cells way more efficient to building incredibly sensitive chemical sensors. But for me, the most exciting part is in medicine. See, silicon is biocompatible, which means our bodies are totally fine with it. So if you can figure out how to make it glow, you suddenly have a completely safe, non-toxic way to light up and actually watch what's happening inside living cells.
So how do you actually do it? Let's start with our first technique. It's basically a kind of chemical drilling, where you use teeny tiny metal particles to do all the hard work. It's got a cool name too, Metal-Assisted Chemical Etching, or MACE for short.
At its core, MACE is really just a super controlled way of causing corrosion. You use what's called a noble metal, think silver or platinum, metals that don't like to corrode themselves, to guide the process of eating away at the silicon. And the really amazing part? It's all driven by pure chemistry. You don't even need to plug it in.
Okay, so here's how it all plays out. You take your silicon wafer and you basically just dip it into this chemical bath. Inside that bath is some hydrofluoric acid and a salt made from a noble metal, say silver nitrate. Almost instantly, little particles of silver start to form and land on the silicon surface. And from there, these particles act like little drills, eating their way straight down into the silicon and carving out these microscopic tunnels.
And this is the incredible result. What you're left with is this perfect, dense little forest of silicon nanowires. These things are unbelievably tall and skinny, which gives them a massive surface area. That's perfect for things like sensors or making solar cells more efficient. It's a truly stunning piece of nanoscale engineering. But there was a catch.
For some of the most exciting applications, especially in bioimaging, scientists realized they needed something more. This super elegant drilling method had one critical flaw that sent everybody back to the drawing board.
And you don't have to take my word for it. The problem is laid out right here in the research. After all that amazing work creating these nanowire forests, they found that the structures did not have emission properties. In plain English, they didn't glow. Not even a little. All that beautiful structure, and it was totally dark.
So you have to ask, why is that such a big deal? For a lot of things, it wasn't. But for one field in particular, it was a complete deal breaker. And here's why. For medicine, making silicon glow is a game changer. Just imagine being able to tag cells with tiny glowing silicon particles. You could watch biological processes happen in real time, all without using the toxic heavy metals you find in other materials like quantum dots. MACE couldn't do that. And so, a brand new quest began. Find a way to make silicon shine.
This challenge pushed researchers to try a totally different playbook. They decided to ditch the metal particle drills and instead use an electric current. The process is called anodization.
Now, anodization is also a corrosion process, but there's a huge difference. This time, electricity is in the driver's seat. You set up the silicon wafer to be the anode, that's the positive terminal, in a little electrochemical circuit. And then you let the electric current do all the carving for you.
So the setup's different, but the goal's the same. Etch the silicon. The wafer goes into a cell with hydrofluoric acid and ethanol. Then you apply a constant electric current, and that current powers a reaction that eats away at the silicon. But instead of drilling straight down, it carves out this complex, tangled network of tiny little pores.
So what happens when you swap out your chemical drills for an electric current? Well, you get a result that was nothing less than a breakthrough. It was exactly what the researchers had been hoping for.
Now check out the texture here. It's totally different, right? It's not that neat, orderly forest of pillars we saw with MACE. No, this is an intricate, porous sponge. It's this beautiful, almost chaotic-looking network of tiny, interconnected silicon crystals.
And that unique, spongy structure, that's the whole secret. It creates this wild physics phenomenon called quantum confinement. Basically, the walls of this sponge are so incredibly tiny that they start to obey quantum rules. They act like little cages for electrons. So when you shine a light on them, the electrons get all excited, but they're trapped. They have nowhere to go. So they're forced to release that energy back out, not as heat, but as their very own little photon of visible light. The structure makes them glow.
And here it is, the payoff. Under UV light, this porous silicon glows with this bright, beautiful, visible light. This is the photoluminescence they were chasing all along. By switching from chemical drilling to electric carving, they had finally done it. They had made silicon that shines.
So, we've got these two really powerful ways to sculpt silicon. Which one's better? Well, the answer is neither of them. It really just depends on what you're trying to build.
Let's just break it down. MACE uses those metal particles to create those tall, orderly nanowires that give you a huge surface area. Anodization, on the other hand, uses an electric current to carve out a spongy structure that glows. They're just different tools for different jobs, leading to completely different but equally amazing results.
The simplest way to think about it is like this. If you need that perfect, ordered forest of silicon pillars for something like a sensor, you grab your MACE, your microscopic drill set. But if what you really need is a glowing silicon sponge for bioimaging, you use anodization. That's your electric carving tool.
And all of this leads to one final, really big question. We've just seen how changing the shape of silicon on this tiny scale can literally make it glow. So it kind of makes you wonder, what other invisible properties are just sitting there, waiting to be unlocked? Not just in silicon, but in all kinds of materials. If only we can find the right tools to carve them.